Welcome to the fourth lecture of this course. In this lecture, we will formally define what it means to say that a DFA computes a string, and we will also look at operations on languages known as regular operations. We will start by looking at the formal definition of computation of a DFA. We gave an informal meaning of what does it mean for a DFA to compute a string in an earlier lecture. Today we are going to look at a formal definition. We will look at a couple of examples after that, and then finally we will end by studying some properties of the languages that are accepted by deterministic finite automata. Okay. So, to begin, let us look at the formal definition of what does it mean for a DFA to compute a string. So, let M be a DFA. So, M equals Q sigma delta Q naught and F. Let me remind. So, here Q is the set of states, sigma is the alphabet, delta is the transition function, Q naught is the start state, and F is the set of accept state. And let W be a string over sigma. Okay, so, W equals, let us say it has n symbols. So, W equal to A1, A2, so on till An, where Ai is a symbol in sigma. Okay. We say that M accepts W if there exist. So, this is the shorthand notation for there exist. I will be using this frequently in this course. So, if there exist, let me write it in bracket for now. A sequence of states R0, R1, R2 up to Rn such that three properties hold. Firstly, R0 is the start state, for all I equal to 1 to up to n, and the third is the acceptance condition, that is Rn belongs to F. Okay. So, this is just a formal way of saying what does it mean to say that a DFA M accepts a string W. So, DFA M accepts a string W if there is a sequence of states, okay, and note here that let me write this, that the states Ri need not be distinct. Okay. So, if there is a sequence of states coming from my set Q such that the first state is the start state, and for every I going from 1 through n, Ri is the state that we get by applying the transition function to Ri minus 1 and Ai. Okay, so, basically R1 will be delta R0 comma A1, R2 will be delta R1 comma A2, and finally Rn will be delta Rn minus 1 comma An. Okay. So, this is basically the transition condition. Okay. So, let me write this here. So, this is the initial condition, this is the transition condition, and this is the acceptance condition. Okay. And the final state Rn is going to be a state that belongs to F. So, this is what we mean to say a DFA accepts a string W. Now, using this, what do we mean when we say that a DFA accepts a language? Okay. So, let L be a language over the alphabet sigma. We say that M accepts L if L equals the set of all strings such that M accepts W. And once again, I should emphasize here that this equal sign is very important. This means that if I look at every string that belongs to this set on the right hand side, okay, so every string that is accepted by M, it belongs to the language L, and whatever string belongs to the language L is accepted by M. Okay. So, it is exactly equal, one is not a proper subset of the other. So, that is very important. And the third is a notation for such type of languages. So, once again let L be a language. We say that L is regular if there exists a DFA M such that L equals L of M. Okay. So, recall from last time, this notation means, so this is another way of saying the language which is accepted by the DFA M. Okay. So, this is just a notation for this language of strings that are accepted by M. So, if there is some DFA that accepts a language L, we say that language is regular. Okay. So, now the natural question that arises is, so of course, we have seen several examples of DFA in our last lecture, and today we will see a couple of more. But more importantly, the question that arises is that are there languages which are not regular? Okay. Is it true that all languages that we have are regular, which means that for every language there is a DFA which accepts it, or are there also certain languages which are not regular, and not only so, can we prove them that they are not regular? So, mathematically can we show that there exist languages for which there is no DFA that we can construct which accepts that language. And as it turns out, the answer to that question is yes, there are languages which are not regular. Let me just state this at this point. So, for example, the language, let me call it L, which consists of all strings of the form 0 to the power n, 1 to the power n, where n is greater than or equal to 0 is not regular. Okay. So, this consists of all strings which have a sequence of zeros followed by a sequence of ones, such that the number of zeros is equal to the number of ones. Okay. So, we will not prove this right now. So, we will in a later lecture we will come back to this language. So, this is going to be a very important language. We will come back to this language and we will prove why this language is not regular, but for the time being I just want to state this. Okay, so now let us look at a couple of more examples of DFA and then we will move to some properties. So, the first example that we will see is let us call it L1, set of strings W such that W does not contain 1 1 as a substring. So, last time we saw an example where we considered strings which contained a certain substring as part of itself. Okay. So, all strings that contained a particular substring. So, today we will look at a language which consists of all strings that do not contain 1 1. How do we construct a DFA for this? So, the idea is going to be as follows. So, we will try to scan the string. Okay. So, when we are reading the string, we try to scan it, and the moment we find a 1 1 present anywhere in the string, we will go to what we call a dump state. Okay. So, we will go to a state from where we cannot actually come out, the DFA cannot escape and come to an accept state any further. Okay. So, let us look at the construction. So, we start at a state Q0. So, if I see a single one, I go to a state Q1, and if I see two successive ones, I go to this state Q2. And now what do these states mean? So, Q2 will correspond to the state where I have seen two successive ones, two ones which are next to one another. So, if I reach Q2, I am going to stay at Q2 no matter whether I see a 0 or 1 after this. Q0 is going to correspond to a state where I have not seen a single one, okay, and Q1 is going to correspond to a state where I have seen just a single one. Okay. So, let me write it here. So, Q2 is corresponds to the set of all strings that contain 1 1 as a substring. Q0 is does not contain 1 1 as a substring and does not end with a 1, and Q1 is going to be that it does not contain 1 1 as a substring, okay, and it ends with a 1. Okay. So, from Q0 if I see a 1, I go to Q1, from Q0 if I see a 0, I will stay at Q0. From Q1, if I see a 1, it means that I have encountered 2 consecutive ones, which takes me to Q2. And if I see a 0 from Q1, it means that the string that I have seen so far does not end with a 1, which means I should go back to Q0. Okay. So, this is the automaton. And what are the accept states of this automaton? So, I want to accept all string that does not contain 1 1. So, it will have 2 accept states. One is Q0 and the other is Q1. Okay. So, in this example, the point that I want to emphasize is that the state Q2 is a what we call a dump state. Okay. So, in other words, so formally if I want to define it, a dump state is a state from where the automaton cannot reach an accept state. Okay. So, if I look at just a couple of examples of strings to this automaton earlier. So, if I look at, let us say, a string 0 1 1 0, okay, sorry 0 1 1 0. What would be the computation of this string on this automata? So, the automaton starts at Q0. From Q0 on a 0, it stays at Q0. Okay. Then again from Q0 on a 1, it goes to Q1. On seeing the third one, the second one, it will go to Q2, and then on seeing the last 0, it stays at Q2. Okay. So, this string makes the automaton end up at Q2, which is not an accept state, hence the string is not accepted. And that should be the case because it does contain 1 1 as a substring. On the other hand, if you look at an example like 1 0 1, what would be the computation? So, on 1, the automaton from Q0, it will go to Q1. On seeing a 0 after 1, it will go back to Q0, and then again on seeing the next one, it will go to Q1. Because Q1 is an accept state, this string is accepted. Okay. Similarly, if you have a string that ends with 0, let us say 1 0 0, you can see that from Q0 it goes to Q1, then from Q1 it will go to Q0, and then it will stay at Q0. Okay. So, this is a string which contains 1 1 as a substring. This is a string which does not contain 1 1 as a substring, but ends with a 1. And this is a string which does not contain 1 1 as a substring and does not end with a 1. Okay. So, another let us look at another simple example. So, let us look at the set of all strings x such that the length of x equals, let us say 3. Okay. So, I want to accept all those strings whose length is 3. So, it is not difficult. So, we start at a state Q0. Now, on seeing the first character, we actually do not care what the characters are, the characters that we see, whether it is a 1 or a 0. So, on seeing the first character, I will just mark it with a 0 1, which means that it does not matter whether it is 0 or 1. I go to a state q1. On seeing the next character, I go to q2, and then on seeing the third character, I go to a state q3, and then after that, no matter what character I see, I will stay at, I will go to a state q4, and I am going to stay there thereafter. Okay. So, whether I see a 0 or a 1, I will not move. So, what are the, so what is my accept state or accept states in this case? So, this state q0 corresponds to all those strings that that have a length 0, which is actually only the empty string epsilon. q1 corresponds to those strings that have length 1, q2 corresponds to those strings that have length 2, and q3 corresponds to those strings that have length 3. So, this is going to be my accept state, and q4 will correspond to all those strings that have length 4 or more. Okay. This is a simple. So, again in this case, if you note, the state q4 is a dump state. Because from q4 I cannot reach an accept state. Okay. So, now we will look at what are called regular operations. Okay. So, there are certain operations, there are some operations that we can apply to languages that gives us some other languages. Okay. So, they can either be binary operations or they can be unary operations. So, a binary operation on languages basically takes two languages and produces a third language, and a unary operation basically takes one language and produces another language. So, the first regular operation that we will see is called the union operation. So, actually these are these operations are something that you have seen even in your middle school, but in the context of languages, nevertheless we will define it. So, so before I define, so let me just mention one thing. So, let A comma B be two languages. Okay, so they can be languages over any alphabet sigma. So, we define A union B in the natural way. So, A union B consists of all strings x such that x either belongs to the language A or x belongs to the language B. Okay. The next operation, so this is something that you have seen. The next is what is called the concatenation operation. So, we denote this with a dot in the middle. So, A dot B is the set of all strings of the form x y such that x belongs to A and y belongs to B. Okay. So, this operation is the concatenation operation where I take two strings x and y and I append one to the end of the other string. So, here x y means that x comes first and then y is appended to the end of x. Okay. So, this operation of concatenation is often also denoted as just AB. So, we just drop this dot in the middle and we just write it as AB. So, as a small example, let us look at this. So, suppose our set A has the elements A and B, and B has let us say 1, 2, 3 and so on. Okay. So, then what is AB? So, AB will consist of all strings of the form. So, first we will have A1, B1, okay, then A2, B2, A3, B3, okay, and so on. Okay. So, this is an infinite languages, this is an infinite language which consists of all those strings that we get by taking one string from A and one string from B and concatenating them. Okay. So, they need not just be, so here I have taken A and B as languages which have strings consisting of a single symbol, but in general they can have more than one symbol as well. Okay. And the final operation that we are going to define today is what is called the star operation. Okay. So, the first two operations, that is union and concatenation, these were binary operations. In other words, these were operations which took as input two languages and produced one language as output. The star operation is a unary operation, it just operates on one language. So, we define A star as the set of all strings of the form some x1, x2, x1 concatenated with x2 up to some xk, where k is greater than or equal to 0 and each xi belongs to A, okay, for all I. Okay. So, basically I take some k strings, okay, and k need not be a fixed number, k can be any number that is greater than or equal to 0. I take k strings and I concatenate them and I just keep on building. So, let us look at an example. So, let A be the language which consists of the strings 1, 0 and let us say 0, 0, 1. Okay. So, then what is A star? Okay. So, in A star, first I look at all strings that I get by taking k equal to 0. So, if k is 0, the only string that is possible is epsilon. Then I take k equal to 1. Okay. So, I look at all strings from A by combining only one string at a time. So, it consists only of the string 1, 0 and 0, 0, 1. Next I take k equal to 2. Okay. So, I combine two strings. So, if A has two strings, the way I can combine these two is in 4 different ways. So, I will get 1, 0, 1, 0 if I take 1, 0 and 1, 0, or I can have 1, 0, 0, 0, 1. Okay. So, if I take the first string with the second string, the third I can get is 0, 0, 1, 1, 0 if I take this first and then I apply the second string, or I can get 0, 0, 1, 0, 0, 1. Okay. And similarly, I can go to 3 strings which are concatenations of 3 strings, 4 strings and so on from A. Okay. So, in particular this language A star is an infinite language if A is some non-trivial language. Okay. So, I will stop here.